Hello everyone, my name is Mattia Segù and on behalf of my collaborators Alessio Tognoni and Federico Tombari, I will present our paper entitled Batch Normalization Embeddings for Deep Domain Generalization. This work has been conducted while all the authors were working at Google. A common paradigm adopted when training deep learning models is that of training them on a set of data points that are originated from a given distribution, and evaluating them on other samples extracted from the same distribution. This works under the assumption that training and test distributions are aligned. We refer to the training distribution as source domain and to the target distribution as target domain. In reality, the assumption that training and test distributions are aligned does not hold true, since the target domain may differ from the source one. We refer to the discrepancy between the training and test distributions as domain shift. For example, we can hypothesize that a deep image classifier has been trained on a dataset containing only photos. However, if we deploy this model on our paintings representing the same objects without adopting any particular expedient, classification accuracy drastically drops. The images that we show here are taken from the PAX dataset, which we also use for evaluating our approach. Domain shift represents a problem that exposes deep learning models to potentially life-threatening failure cases when deployed in the continuously changing environment presented by the real world. As such, domain shift needs to be addressed for multiple reasons. First, it exposes deep learning models to failure cases when deployed on domains that were not seen during training. Second, typical deep learning solutions require to retrain a model on another domain so that it performs well also on the latter. This can be expensive and time-consuming. Finally, collecting data under a huge variety of conditions can be expensive and prohibitive for most users. The real world is continuously evolving, and we cannot expect a dataset to represent all possible testing scenarios. We now define domain generalization, the specific setting addressed by our work. Domain generalization attempts to address the domain shift problem by learning from multiple sources models that are able to generalize to unseen domains. Contrary to domain adaptation, domain generalization assumes that no knowledge from the target distribution is available during training. Take for example the PAX dataset, which is divided into 4 different domains: our painting, cartoon, photo, and sketch. We can assume that 3 source domains are available during training, for example cartoon, our painting, and photo. Domain generalization aims at reducing the effect of domain shift on the left-out domain, sketch in this case, and improve the generalization of a deep learning model. Traditional domain generalization methods typically aim at learning domain invariant representations that can extend to unseen domains. However, while this paradigm has proven to be effective in some cases, it forces the model to discard domain-specific attributes, a key piece of information that we believe can be exploited to further boost domain generalization. In our work, we propose to leverage domain-specific information to map source domains to a same latent space, so that distance awareness between domains and new instances is achieved. The resulting domain space can be used to interpolate the learned domain-specific distributions and hallucinate the distribution of the unknown domains. In particular, we observe that samples from different domains can be clustered in the feature space of a deep neural network according to their instance statistics. Consequently, domain-specific population statistics can be used as centroids to represent each source domain seen during training. Unknown samples from any known or unknown domain can thus be projected to the same latent space by means of their instance statistics. A distance measure between the embedding of the previously unknown instance and that of each known training domain can thus be computed in the proposed latent domain space. We propose to use the so-computed distances to combine the learned training distributions and estimate the test one. We now present the mapping strategy that we propose to project training and test domains into the same latent space. In order to collect domain-specific population statistics to represent domain embeddings, we propose to rely on multi-source domain alignment layers. A multi-source domain alignment layer is composed of one batch normalization layer for each source domain, and maps a feature space to a normalized feature space according to the population statistics of the assumed input domain. Given a deep feature extractor, we plug a multi-source batch normalization layer after every convolutional layer. All weights in the neural network are shared, except domain-specific batch normalization parameters. This allows to update and collect domain-specific population statistics for each source domain during training. Predictions for samples of which the domain label is known are thus computed by propagating them through the corresponding domain branch. If we consider once again the PAX dataset with our painting, cartoon, and photo as source domains, this would result in a multi-domain batch normalization layer with distinct batch normalization branches for each source domain. At every level in the network, the domain-specific population statistics allows to map all source domains into the same latent space. At inference time instead, we receive a sample from an unknown domain. We propose to use instance normalization to propagate this sample through the feature extractor and use instance statistics to map it at each level of the neural network in the corresponding domain space. Since we left out the sketch domain during training, at test time we receive a sample from this domain. Instance normalization allows us to map this sample into the same latent space with respect to the embeddings of the known domains. Thanks to the proposed mapping strategy, all training domains and the new instance are mapped to the same latent space at every level in the network. We propose to use the Wasserstein distance between the embeddings of source distributions and distance embeddings to estimate the predictive distribution of the unknown domain as a linear combination of known ones, where the sum of the reciprocal of the distances at each level of the network is used as weight for the combination. Analogously, we can compute the final prediction as the linear combination of predictions for the test sample obtained under different domain assumptions. Moreover, we observe that when this strategy is replicated at training time also for samples from the source domains, the learned latent space are more meaningful and allow for better generalization. We refer to the application of the same mapping strategy also training time as distance training. We compare B and E against several competitors on the PAX dataset using ResNet 18 as backbone. First of all, we term our method B and E after its main component, the proposed batch normalization embedding. We also compare to dpol, the baseline obtained by training on the merged set of source domains. Different columns correspond to different leave one domain out settings, meaning that we assume the corresponding domain to be unavailable during training and train on all other sources instead. To validate the generalization performance, we then report the accuracy on the domain that wasn't seen during training. Since different methods rely on different initializations of model weights, we report for every competitor the performance on each leave one domain out setting, the average performance of the baseline dpol, the average performance of the method itself, and the relative gain with respect to the baseline. We show that B&E outperforms several competitors and achieves competitive results on all domains. To further validate the effectiveness of our proposal, we train a ResNet 18 on PAX and analyze the classification accuracy obtained on the left-out domain when each sample is classified only using the closest, the second closest, or the third closest domain branch. As expected, performance decreases when we classify samples using the prediction branch corresponding to domains that our method judges further in the proposed latent space. We can finally summarize the contribution of our work. We propose a novel mapping strategy of domains and instances to a same latent space using batch normalization embeddings, which we leverage to improve generalization. We hope that future work will continue to investigate the properties of domain-specific information and their combination with traditionally used domain invariant representations to boost domain generalization. Thank you very much for listening to this presentation. In case you have any questions, please don't hesitate to ask them in the comments section below.